Welcome back to the deep dive. Today we are strapping in for a high-speed, high-stakes journey. We're going deep into the secret sauce of modern communication. I'm talking about hidden algorithms that keep, terabits of data flowing across channels that, frankly, look electrically unusable. Our mission today is a really deep technical dive into the core of high-speed serial communications. So the SerDes receiver, we're moving way past the block diagrams. We're going to look at the mathematical engines that power things like 400G and 800G Ethernet links, especially those using multi-level pulse amplitude modulation or PAM4. And these links, they're a constant battleground against noise and distortion. We've collected a massive stack of sources detailing both the time-tested classical signal processing algorithms and the really cutting-edge machine learning approaches that are fighting this war for digital clarity.
And we absolutely have to start with the enemy. This entire deep dive, everything we're going to talk about today is driven by one core, relentless, and frankly, unforgiving physical phenomenon.
Intersymbol interference.
Intersymbol interference, or ISI. It is the fundamental limit of high-speed signaling. ISI happens because the channel, and that could be a copper trace on a circuit board or a long stretch of fiber, it basically acts as a low-pass filter. So when the transmitter sends out a symbol pulse, that pulse spreads out in time because of the channel's frequency-dependent attenuation. Instead of a nice, clean, square wave, the pulse gets this long, decaying tail.
And that tail overlaps with the next symbol.
It overlaps and corrupts the neighboring symbols being transmitted right behind it.
So if you're trying to read the signal voltage for, let's say, symbol N, you're not just measuring N, you're measuring the leftover unwanted voltage from symbols N-1, N-2.
And maybe even M+1 or M+2.
Right, because of the channel's memory. It's like a digital haunting where the ghosts of past and future symbols are constantly messing with the present decision.
That's a perfect way to put it. To put a mathematical frame on it, the messy analog signal we get at the SerDes input is a convolution. It's the convolution of the clean, transmitted symbol sequence with the channel's own specific impulse response. And our job, the entire purpose of the SerDes receiver, is to perform this incredibly complex, multi-layered deconvolution and decision process in microseconds.
All to hit that post-FEC error rate of 10 to the minus 15.
Exactly. And that target, especially with PAM4's 4 very tightly spaced voltage levels, is what dictates the incredible complexity we're about to dig into.
Okay, so let's unpack this. Our goal today is a comprehensive, layered look at how these receivers pull off that practically impossible feat. We're going from the initial analog conditioning through these highly optimized adaptive digital filters, and finally to algebraic error correction.
The mission is to understand the hierarchy of defense. We'll see how every subsystem has a special job. We start with low complexity analog steps that, prevent noise from getting amplified in the first place.
And then we move into the digital world.
Right. Into digital adaptive algorithms that follow the channel as it drifts, and we finish with these complex sequence detectors and even machine learning optimizers that are continuously fine-tuning the final decisions.
We begin right at the receiver input, where the signal is still purely analog. Before we even think about turning this into ones and zeros, there are critical steps taken to make the digital processing job even possible. What are those first lines of defense?
This is the mixed signal domain, and you're right. If you fail here, everything downstream is guaranteed to fail. We focus on 2 steps that happen either at the same time or right before the signal hits the main A to D converter.
And those are?
ADC calibration, or ADCCL, and the continuous time linear equalizer, the CTLE.
Okay, let's start with ADCCL. This sounds a bit like basic preventative maintenance, but given how little voltage separation there is between PAM4 levels, I have to imagine an uncalibrated ADC is basically a death sentence for the link.
It's absolutely fundamental. Think about PAM4. You have 4 levels, usually normalized to -3, -1, +1, and +3. The voltage difference between any 2 adjacent levels is tiny, just 2 unit voltages. So any error in the ADC's measurement is going to be a huge problem.
Right, because your margins are already razor thin.
Exactly. And ADCs, especially the high-speed ones that are often dealt with a time-interleaved architecture, where you have multiple physical ADC slices running in parallel to boost the sampling speed, they suffer from 2 main problems: DC offset error and gain error. The gain error is particularly nasty in time-interleaved ADCs because each slice might have a slightly different gain. So the exact same input voltage gets interpreted differently by adjacent slices. That's gain mismatch.
And ADCCL is the mechanism that neutralizes this.
Correct. The mechanism is a closed-loop measurement and correction process. During startup, or calibration phase, the ADCC block applies a known controlled input, maybe a slow DC sweep or a ramp, and it measures the raw output. Using basic linear regression, the system estimates the actual gain, let's call it G hat, and the offset, O hat, of the ADC's transfer function.
And then it just corrects for it.
It then applies a digital correction to all the raw samples before they're passed to the equalizers. The formula is simple. The corrected output is the raw ADC output minus the offset, all divided by the gain.
So it's just normalizing the output, is making sure the entire system starts with a pristine, level playing field.
Absolutely vital. And the relevance here is profound. An uncorrected DC offset shifts all the decision thresholds in your PAM4 slicer. Yeah. So if your decision boundaries, which are supposed to be centered at -2, 0, and +2, all shift by just 10 millivolts, your already tight margins are just destroyed. You get an immediate massive degradation in the raw bit error rate. ADCCL makes sure the digital processing starts with accurately represented data.
Okay, so once that signal is calibrated, it moves on to the second major analog component, the CTLE. This is where we start physically fighting ISI before the signal even turns digital. Why do we need an analog filter here? Why not just do everything digitally after the ADC?
That goes right back to the physics of the channel. In a copper trace, you have two major losses that dominate at high speeds. There's the skin effect loss, where current crowds near the surface, increasing resistance at high frequencies, and dielectric loss, where the PCB material itself absorbs energy.
And both get worse with frequency.
Both create a severe low-pass filtering effect. The CTLE is an analog peaking filter that's applied before the ADC specifically to compensate for this. It introduces a boost at the high frequencies, basically trying to invert the channel's low-pass response.
And doing this in the analog domain gives us some big advantages.
Two major system benefits. First, we significantly reduce the ISI before we even digitize the signal. This means the digital blocks that come later, like the FFE, have less work to do and need fewer taps. Second, and this is critical, we limit noise boosting. If we had to rely on a really long, high-gain digital FFE to fix a massive channel loss, that digital filter would amplify high-frequency noise right along with the signal.
And your signal-to-noise ratio would be ruined.
Catastrophically. So by using the CTLE, we mitigate the worst of the loss and the noise before the digital domain ever sees it.
I get the goal, but the sources imply the CPLE design itself is far from simple. It's not just a single knob you turn. It's described as a multi-stage, highly configurable filter.
And that complexity comes from the need for flexibility. You need to handle all sorts of different channel lengths and materials. Our sources detail a typical two-stage design. Stage 1 is the core equalizer. It uses complex transistor circuits to create 3 parallel signal paths, low, mid, and high frequency control, each with switchable parts to provide discrete gain steps, maybe half a dB or 3 dB per section. Combining these paths gives you a really high resolution, say, half dB steps in the overall frequency response.
That's the second stage.
Stage 2 provides wideband gain and, more importantly, continuous analog tuning for tracking small environmental changes. It gives you a fine-grained plus or minus 1 dB adjustment range when you're in tracking mode.
The really tricky part seems to be picking the best configuration. The sources mention 87 valid combinations. Wait, 87? How does the firmware possibly decide which of those 87 settings is the best balance between correcting ISI and not boosting too much noise?
Right, that's the CTLE selection challenge, and it happens during the acquisition, or ACQ phase. The firmware doesn't brute force test all 87, it's much smarter than that. First, the firmware will often take a snapshot of the received signal and run a fast Fourier transform, an FFT. This shows the channel's current frequency response.
So it can immediately rule out a bunch of bad choices.
Exactly. It lets the firmware quickly shortlist the combinations whose peaking curves best match the inverse of what it's seeing from the channel. This takes the search space from 87 down to maybe 10 or 15 candidates. Then second, the firmware enters an SNR ranking phase. For each of those shortlisted settings, the system briefly runs data and measures a proxy for the quality of the eye opening, often the Q factor, or a preliminary BER estimate.
And the Q factor is just a measure of signal level versus the noise and ISI combined.
Correct. The firmware picks the CTLE setting that gives the highest Q factor. This ensures you get the equalization you need with the least amount of noise amplification. It's a critical initial optimization step that can take hundreds of milliseconds during link training.
That makes perfect sense. It really highlights that the analog-digital handoff is where the first big computational decisions are made. The CTLE is that crucial preconditioning step that gives the digital processor a fighting chance. Because if you amplify too much noise at this stage, no amount of digital magic can save the signal later on. Okay, so once that CTLE conditioned signal hits the analog to digital converter, it's finally a stream of digital samples. Now the core job begins: digital equalization. What's the fundamental theory we're applying here to get rid of the rest of that ISI?
Like we said before, the foundational theory is mathematical inversion. We're trying to implement a digital filter, let's call it E of Z, that's designed to be the inverse of the channel response, H of Z. The goal is that the resulting cascaded system response, H total of Z, which is just E of Z times H of Z, is as close to unity as possible, a single delta function.
Meaning the ISI terms are just gone.
Completely eliminated.
And the classic tools for this job are the feed-forward equalizer, the FFE, and the decision feedback equalizer, the DFE. Let's break down the FFE first.
The FFE is a linear finite impulse response, or FIR, filter. It operates directly on the sequence of digital received samples, Y of n, and because we're talking about high-speed links, the FFE typically operates at the symbol rate.
So it's a linear filter. What does that mean in practice?
It means it's pretty simple to implement. You just tap delayed versions of the input signal, multiply them by some coefficients, we call them taps, and then you sum them all up. And because we buffer the received sequence, the FFE can use taps that correspond to samples received before the current cursor. Those are precursor taps, and samples received after the cursor, the post-cursor taps.
Which makes it really good at dealing with precursor and mid-cursor ISI.
Very effective.
But how are those tap coefficients actually determined? You mentioned zero forcing earlier, is that it?
That's one of two main methods. The simpler one is the zero forcing concept. The tap coefficients are calculated to literally force the total channel impulse response to zero at all sampling times except for the main cursor. It's simple, but it assumes the channel is deterministic and it has a nasty habit of amplifying noise.
Okay, so what's the better way?
The better method, especially for noisy channels, is minimum mean square error, or MMSE, equalization. Here, the tap weights are chosen to minimize the power of the residual error after equalization. MMSE is superior because it finds that optimal trade-off between canceling the ISI and suppressing the noise. And in practice, the adaptive algorithms we'll talk about later, specifically LMS, are used to continuously find these optimal MMSE tap values in real time.
But even with all its flexibility, the FFE still has a key theoretical limitation when it comes to post-cursor ISI.
That's the critical drawback of any linear equalizer. The FFE cannot perfectly cancel post-cursor ISI without a massive amount of noise boosting.
Why not?
Because post-cursor ISI is the result of the current transmitted symbol bleeding into future symbol slots. To cancel that linearly, you'd have to crank up the gain like crazy, treating those ISI terms as part of the desired signal, and that just brings in an unacceptable amount of noise.
So we need a non-linear approach, something that understands what the transmitted symbols actually were. And that brings us to the decision feedback equalizer, the DFE.
Correct. The DFE is nonlinear, and it operates using a feedback loop. Its genius is that it uses the hard-passed slicer decisions, the estimated symbols, S hat of n minus k. So once the slicer has confidently decided what the symbols n minus 1, n minus 2, and so on were, the DFE just assumes those decisions are correct.
And then it uses that information to predict the ISI.
Exactly. It uses a feedback filter with coefficients bk to calculate exactly how much ISI those confirmed previous symbols should have caused on the current sample, y of n. And then it just subtracts that estimated ISI from the FFE output.
So the equation's key here. The DFE output is the FFE output minus this sum of feedback coefficients times the past decisions.
That's the one, and you can see the huge advantage right away. If your past decisions are correct, the post-cursor ISI is removed perfectly, and you do it without any noise boosting, because the DFE is subtracting a clean, noise-free estimated ISI component.
That sounds almost too good to be true. It offers superior performance, especially in those really high-loss channels you see in 800G applications. But this power introduces its primary danger.
Error propagation.
Wait, if error propagation is such a huge risk, a wrong decision cascading into a whole stream of future wrong decisions, why wouldn't we just use a much longer FFE instead? Even if it adds some noise, why take that risk?
That's the core engineering trade-off. We accept the risk because the performance gain from the DFE is often mandatory to meet the required BER. An FFE long enough to cancel severe post-cursor ISI would need such enormous high-frequency gain that the noise floor would just be pushed right above those tight PAM4 margins.
So you'd just be swapping ISI for amplified noise, which is just as bad.
It's just as fatal. So we manage the DFE risk through design. First, DFE systems are designed with high confidence in the first few tacks, since errors there are the most likely to propagate. Second, you can use techniques on the transmitter side like partial response signaling or symbol-level precoding. And third, by coupling the DFE output to a sequence detector like MLSE, which we'll get to next. The system can actually go back and correct for isolated DFE errors retroactively. It can break the propagation chain.
That context is crucial.
Okay.
Let's talk about one more specific noise cleanup block, the noise suppression slicer, or NSS. This seems like a filter designed to fix the side effects of our other filters.
That's a great way to put it. The filters we just discussed, the CTLE and the FFE, they're essential, but they have a side effect. They take the originally flat or white noise and they reshape it. The noise at the final slicer input is now correlated in time. It has a colored power spectral density.
And the NSS takes advantage of that correlation.
Precisely. The insight is that if the noise component at time n is correlated with the noise at time n-1, and we know the total error at n-1, which is just the difference between the equalized sample and the hard decision, we can use that information to predict and cancel part of the noise at time n.
So it's using the error from neighboring samples to clean up the current one.
Yes. The NSS uses the slicer error of its neighbors to estimate the current correlated noise contribution and then subtracts it just before the current sample decision is finalized. It's a sophisticated adaptive residual noise canceller. It's making sure the noise components that were introduced by the equalization chain don't unnecessarily push symbols across those tight PAM4 thresholds. So we've established that classical equalization, your FFE and DFE, cleans up the signal a lot, it reduces ISI and mitigates noise. But even after all that, the final step in a traditional receiver, which is just slicing, is fundamentally suboptimal in these deep ISI environments.
And here's where it gets really, really interesting for me. Why is the act of simple symbol-by-symbol slicing, just picking the nearest PM4 level, considered suboptimal if the FFE and DFE have already done their job?
It's the context limitation. A slicer is memoryless. It only uses the current sample, y of n, and compares it to a set of fixed thresholds. It completely ignores the known reality of the channel, which is that symbols n-1 and n+1 still have some influence on n.
So when noise pushes a sample right near a threshold,
A memoryless slicer has to make a 50-50 guess based on that noise spike.
and that's where maximum likelihood sequence estimation, or MLSE, comes in.
It fixes this by incorporating the channel's memory directly into the decision process. Its core goal is sequence estimation. It's trying to find the single most likely entire sequence of symbols that, if you passed it through the known channel response, would result in the specific received signal you're seeing. So mathematically, assuming the leftover noise is Gaussian, MLSE is looking for the sequence that minimizes the accumulated squared error between the received signal and the modeled signal over a long window. It formally integrates the ISI cancellation into the decision itself.
That seems like the only truly robust way to make a decision. But we quickly run into what you call the brute force nightmare, checking 4 to the power of 100 possibilities if the sequence is 100 symbols long with PM4. It's impossible.
It is completely impossible. And that's why MLSE was just a theoretical curiosity for a long time, until the Viterbi algorithm provided the key. Viterbi is a phenomenal example of dynamic programming that exploits the physical reality of the channel. The core constraint that Viterbi uses is the channel's finite memory, let's call it L. If the channel's impulse response is only non-zero for, say, L symbol periods, then the ISI affecting the current symbol only depends on the last L-1 transmitted symbols.
So instead of tracking the entire history of 100 symbols, we only need to track the very recent past, right?
Exactly. We define a state, sigma of n, based only on those last L-1 symbols. Since we're using PAM4, the number of possible states is fixed at m to the L-1, or 4 to the L-1.
So if our FFE has already reduced the effective memory down to, say, L equals 3, then the number of states is just 4 squared, which is 16.
16. Suddenly, it's manageable.
Okay, so how does the algorithm actually work with these states?
The Viterbi process has two main phases. The forward pass iterates through time, symbol by symbol. At each step, it calculates a path metric, which is just the accumulated error for every possible transition to every state. And since 2 or more paths might lead to the same state, Viterbi does something brilliant. It selects only the path with the lowest accumulated error, the survivor path, and it just discards the rest. It also stores a backtrack pointer that remembers which previous state led to this optimal current state.
And once it gets to the end of the sequence,
Once the whole sequence is processed, the backward pass, or traceback, begins. It finds the state with the minimum overall metric at the very end, and then it uses those stored pointers to trace its way back state by state to the beginning. And that recovers the single most likely transmitted symbol sequence.
that's incredible. It reduces the complexity from that impossible exponential number down to a polynomial one, which makes high-performance detection actually practical for SerDes.
It's the power of dynamic programming.
But even with that amazing complexity reduction, MLSE must still introduce some significant hardware challenges, right? I'm thinking latency and power consumption.
It absolutely does. The most immediate challenge is latency. You can't even begin the traceback process until you've received and processed a whole block of symbols, n, to guarantee that the paths have all merged. This forces the receiver to buffer a long sequence of samples, which creates non-trivial latency compared to a zero latency hard slicer.
And the complexity, while manageable, still grows exponentially with that effective channel memory, L.
It does, and that is the primary reason that MLSE is almost never run on the raw, highly distorted channel. It's used in what we call hybrid detection architectures.
Right, where the FFE and DFE do the first pass.
Exactly. They perform the coarse, noise-efficient cancellation, and that effectively reduces the channel memory L from maybe 10 or 12 down to a much smaller L prime, like 2 or 3.
And then MLSE takes over.
Then MLSE takes over, using Viterbi with a small fixed number of states, maybe 16 or 64, to optimally decode the residual ISI and noise that the linear filters left behind. And that combination gives us near optimal performance with practical buildable complexity.
So we have these really powerful fixed filters, the FFE, the DFE, the MLSE, and they get configured for the channel during startup. But we know real-world channels are dynamic. Temperature changes, aging silicon, supply voltage variations. It all means the optimal setting for those filter coefficients is constantly drifting. A static solution is just destined to fail. And this brings us to the adaptive core of SerDes, the least mean squares, or LMS algorithm.
LMS is the engine of sustained performance in SerDes. Its entire purpose is to continuously minimize an error metric in real time, keeping the equalizer perfectly aligned to the changing channel. Without it, the link would probably fail within minutes of any environmental change. The objective of LMS is to find the optimal set of filter weights, let's call it a vector W, that minimize the mean square error, or MSE. The MSE is just the average squared difference between the desired symbol and the actual output of the filter.
But calculating that true average, the exact statistical gradient, is way too slow and computationally demanding for high-speed hardware. And that's the genius of the LMS simplification, isn't it?
It's the elegant compromise that made LMS an industry standard. Instead of the exact gradient, LMS uses the instantaneous gradient calculated from a single sample's error. It's a form of stochastic gradient descent.
And its strength is its simplicity.
It really is. The core update rule is beautiful. The new weight vector is the old weight vector plus some step size, mu, times the error, times the input vector. That's it.
Just simple multiplication and addition per tap.
Which means its complexity is low. It's O of n, where n is the number of taps.
And that step size, mu, that's where the critical trade-off lives. It seems like the single most important tunable parameter in the entire adaptive system.
It absolutely is. Mu controls the rate of adaptation. If mu is small, the filter is highly stable. It moves slowly, it's not easily perturbed by noise spikes, but convergence during initialization is slow, and you get a higher misadjustment, a larger steady-state error because it never quite reaches the true minimum.
And if mu is large?
If mu is large, the filter adapts extremely fast, which is great for rapid link initialization, but it leads to a very high misadjustment. The filter is constantly overshooting the minimum point, which results in a lot of steady-state noise in the tap weights.
So you probably use a schedule for it.
Almost always. SerDes systems often employ a schedule where mu starts out large for fast acquisition and then it shrinks dramatically for stable tracking.
Now, you mentioned complexity. We touched on RLS recursive least squares earlier. It often converges faster and has lower misadjustment, but it's rarely used in high-speed copper or optical SerDes. Why does the industry overwhelmingly choose the slightly lower performance LMS?
It all comes down to the hardware implementation cost. RLS requires computing and inverting a correlation matrix, which means its complexity scales as O of n squared, where n is the number of taps. LMS is strictly O of n.
And in a high-speed ASIC running at 50 plus gigahertz, O of n squared translates to
Exponentially higher power consumption, a significantly larger silicon area. You need massive hardware blocks for matrix math and higher clock latency. For a 16-tap FFE, n squared means you're computing 256 matrix elements for every single update. LMS only needs 16. The cost and power penalty of RLS usually just outweigh the marginal performance improvement. It makes LMS the pragmatic choice for volume chip design.
Okay, so LMS handles the continuous, steady adaptation of the major filters. But that adaptation rate, even in tracking mode, is still tied to a statistical average. What handles the high-frequency immediate microdrifts that LMS might be too slow to catch?
That's where the continuous adaptive slicer, or CAS, comes in.
The hardware panic button.
The hardware panic button for threshold stability. That's a good name for it. As we said, environmental factors cause rapid voltage shifts. A 5 degrees Celsius change can shift your signal levels by 50 millivolts. The slow firmware tracking, which runs at just a few hertz, cannot react to distortion flutter that can reach 1 or 2 megahertz, caused by things like power supply ripple or localized temperature gradients.
It's like you're driving a car at 100 miles an hour, and your steering wheel is continuously adjusting for every tiny ripple in the road. That's CAS fighting the flutter.
That's an excellent analogy. CAS is a dedicated hardware block that's designed to run autonomously and very rapidly. It operates after the FFE and DFE have cleaned the signal. Its only job is to make sure the PAM4 slicer thresholds are perfectly centered on the incoming signal levels.
And how does it do that so quickly?
It achieves this by continuously accumulating two crucial statistics using low-complexity infinite impulse response, or IIR, averaging. It measures the average offset, which is proportional to the expected value of the error, and the average gain, which is proportional to the expected value of the error times the estimated symbol.
So the offset tells it if the whole constellation is shifted up or down.
And the gain statistic tells it if the symbol levels are compressed or expanded.
Right.
These statistics are then used to generate a continuous analog voltage correction that's applied directly to the slicer thresholds. And because CAS is a dedicated local hardware loop, it operates orders of magnitude faster than the central firmware. It ensures the decision boundaries are stable against that fast environmental noise, preventing temporary threshold crossings that could cause a burst of uncorrectable errors. We've broken down all the components, but a SerDes receiver success is really measured by the seamless integration of these blocks. We need to zoom out a bit and see the complete pipeline, which also means we have to look at the complementary steps on the transmitter side and, of course, the all-important timing recovery.
Okay, so lay out the full processing stack for us. Give us the data flow from start to finish.
It's a cascade of corrections. It starts with the analog input, which goes to the CTLE for analog peaking, then to the ADC for digitization and ADCCL.
Then the digital filters.
Right. Then to the adaptive FFE for pre- and mid-cursor ISI cancellation with its taps tuned by LMS. Then to the DFE for post-cursor ISI cancellation, its coefficients also tuned by LMS.
After that comes the CAS.
So in the CAS for continuous threshold tracking. And finally, to the slicer or MLSE for the final decision, and then off to the FEC decoder. And as we touched on earlier, a modern, power-optimized system almost always runs hybrid detection. This is the key to balancing performance and complexity.
Remind us why that combination is so much more effective than using just one or the other alone.
Well, if we only used MLSE, the complexity would be way too high because of that long channel memory L. But if we only used FFE and DFE, we'd be limited by the DFE's error propagation risk and the suboptimal nature of hard slicing when you still have residual ISI and colored noise.
So hybrid detection resolves this.
Exactly. The LMS, adapting the FFE and DFE, performs the coarse ISI suppression, and that reduces L significantly. Then, MLSE, with its optimal Viterbi algorithm, takes that reduced memory signal and performs the fine sequence estimation. This lets the system achieve near Shannon limit performance, the theoretical maximum data rate for a given noise level, with practical hardware size and power.
Now, we've focused almost entirely on the receiver cleaning up the mess. But modern systems believe in preventative medicine. Let's look at the transmitter side solution, digital pre-distortion, or DPD.
DPD is a transmitter side technique that's essential for maintaining signal quality, especially at high power levels or when you're driving long channels. The core problem it solves is the non-linearity of the output stage, usually the power amplifier, or PA. When you drive a PA close to saturation to get better efficiency, it introduces non-linear distortion. You get AMM, where amplitude input affects amplitude output nonlinearly, and AMPM, where amplitude input affects the phase output nonlinearly.
And this distortion causes signal levels to spread out, creating unwanted out-of-band energy.
Which is known as spectral regrowth. The DPD solution is really elegant. You apply the inverse nonlinearity to the digital signal before it even enters the PA. The ideal cascade is your input signal goes into the DPD, then the PA, and what comes out is a perfectly linear, scaled version of your original input.
And DPD requires a precise model of the PA's behavior to do that.
It does. A common model is the memory polynomial. This model captures both the instantaneous nonlinearity, which is the polynomial order k, and the fact that the nonlinearity depends on previous samples, which is the memory depth m.
Why is that memory depth m needed? If it's just nonlinearity, shouldn't a simple polynomial be enough to model it?
M is needed because the nonlinearity is often dynamic, it's not static. The amplifier's impedance, its gain, its thermal state, they all have a memory of past signals. If you send a sequence of high-amplitude pulses, the amplifier might react differently to the 10th pulse than it did to the first. The memory polynomial captures this dynamic effect, and it requires adaptive learning. Those coefficients are often learned using an external feedback loop, typically employing the LMS algorithm, which minimizes the error between the desired linear output and the actual distorted output. Then it adjusts the pre-distortion coefficients accordingly.
Okay, let's shift focus entirely to timing. All these complex filters and decisions are completely useless if the data is sampled at the wrong moment. And this is the domain of the Clock and Data Recovery Unit, the CDR.
CDR is absolutely mission critical, particularly with the tight timing margins of 100 plus gigabaud signaling. It has to recover the exact frequency and phase of the transmitter clock from the noisy, distorted data stream itself. The CDR has two main parts: the clock recovery unit, or CRU, and the phase interpolator, or PI. The CRU is typically a phase-locked loop with a crucial loop filter, which is often implemented as a proportional integral, or PI, controller.
And that PI controller structure is designed to balance speed and accuracy.
It is. The proportional term, KAP, provides immediate correction based on the current timing error, which ensures a fast response to jitter. The integral term, KII, accumulates the timing error over time. And this integral action is what allows the CRU to track slow frequency differences between the transmitter and receiver clocks.
Right, to meet the standards that require tolerance for plus or minus 500 parts per million frequency drift.
Exactly. And the control output is just the sum of these two terms, dictating the necessary phase shift.
And the phase interpolator, the PI, takes that continuous control word and turns it into an actual physical clock signal for sampling.
Correct. The PI is the execution block. It generates the final sampling clock with phenomenal precision, often achieving sub-UI precision. A unit interval is the period of one symbol.
So for a 106.25 gigabaud link, the UI is about 9.4 picoseconds, and the PI often has a resolution down to 1 picosecond or less.
It does this by generating many equally spaced reference phases, typically 32 or 64 phases derived from a high-quality reference oscillator. When the CRU demands a phase shift that falls between two of those adjacent reference phases, the PI linearly interpolates between them using weighted current summing.
So it can continuously and smoothly adjust the sampling instant.
To always land exactly at the center of the received eye diagram, maximizing the timing margin for the slicer.
Even with that brilliant equalization and sub-picosecond timing, the residual noise on channels that are operating right near their physical limits means that some errors, random bit flips, or short burst errors will inevitably happen. And this necessitates the ultimate digital safety net, forward error correction, or FEC. Let's talk about the mandated standard for 400G and 800G.
The IEEE 802.3DJ standard requires a hierarchical FEC architecture, and that's because no single code can efficiently handle both random single-bit errors and large burst errors at the same time, while also meeting that ultra-demanding post-FEC BER target of less than 10 to the minus 15. This is the final layer of defense.
A hierarchy with two levels.
Two levels. We start with the inner FEC, which operates at the PMA level, right close to the PAM4 slicer. This later might use a simpler code, like a Hamming code, or a short high-rate soft decision code. Its job is to handle that dense field of raw, single-bit errors. And crucially, this layer often leverages LLRs, or log likelihood ratios. So instead of the slicer only reporting a hard decision, was it a +1 or a -1, LLRs report a confidence score. They tell you how far the received sample was from the decision boundary.
How exactly does that soft decision information give us an advantage over a hard decision?
It provides a significant coding gain, typically around 2 dB. Imagine a sample lands just 1 millivolt away from the decision threshold. A hard slicer says it's a 1. An LLR-based soft slicer says it's a 1, but I'm barely sure about it.
So it has a low LLR score.
A low LLR score. If the decoder then finds that the resulting code word has an error, It knows to focus its correction efforts on the symbols that had those low LLR scores first. This informed guessing dramatically increases the probability of correct decoding compared to just treating every error equally. That's where we get that 2 dB gain in effective SNR.
And the second, higher layer.
The second higher layer is the outer FEC, which handles larger errors and burst errors. For the standard, this is the KP4 Reed-Solomon, or RS, code. The specific code is RS 544-514-15, and it's defined over the Galois field GF2 to the 10.
Okay, let's pause on the math there. What does it mean for the code to be defined over a Galois field? GF2 to the 10. Why not just use standard binary math?
This is fundamental to modern coding theory. GF2 to the 10 means the symbols are 10 bits wide, and all the arithmetic addition multiplication is performed using polynomials with coefficients from the binary field GF2.
So it's basically arithmetic performed modulo an irreducible polynomial.
Right. The result is that these 10-bit symbols behave like algebraic units in a finite field.
And the RS 544-514-15 definition
Means n equals 544 total 10-bit symbols in a code word. K equals 514 are the information symbols, and the other 30 are the parity symbols. And those 30 parity symbols allow the code to correct up to t equals 15 symbol errors per code word. It makes it extremely robust against burst errors.
Decoding this code sounds like an intensive algebraic process.
It is. It involves a sequence of 4 classical steps. First, syndrome computation. This calculates the remainder when the received polynomial is divided by the generator polynomial. A non-zero remainder, a syndrome, indicates errors.
And gives the signature of those errors.
Correct. Second is the Berlekamp-Massey algorithm. This uses the syndrome to find the error locator polynomial, which is a polynomial whose roots correspond to the locations of the symbol errors. Third is the Chan search. This is a simple, high-speed root-finding process that just tests all possible symbol locations to find the specific roots of that error locator polynomial, confirming the location of the errors. And finally, fourth, Forney's algorithm. This step takes the error locations and the syndrome values to calculate the exact magnitude of the error at each location, which allows the symbol to be corrected perfectly.
That is an immense amount of complexity just to fix 15 10-bit symbols. It's a full algebraic engine working alongside all the signal processing filters. Now, before the FEC, we rely on gray coding and differential precoding.
Gray coding is absolutely non-negotiable for PAM4. Since PAM4 uses 4 closely spaced levels, noise usually only causes errors between adjacent levels, like a +1 being misinterpreted as a -1. Gray coding maps those adjacent voltage levels so that their corresponding binary counts differ by only 1 bit. This is crucial because it converts a high-probability symbol error into a low-probability single-bit error, which makes the FEC much more efficient.
And differential precoding.
Differential precoding, or PDC, addresses phase ambiguity. Receivers can sometimes lock onto the signal 180 degrees out of phase. PDC makes the current symbol dependent on the previous one. It ensures that even if there's phase ambiguity, the difference between symbols stays the same.
And in the stop decision inner FEC, it also lets you combine the LLR reliability info from 2 consecutive symbols,
which further boosts the effective SNR.
Finally, we need to test all of this. How do we stress the system to ensure it's compliant? That requires the deterministic randomness of a pseudo-random bit sequence, a PRBS.
PRBS sequences are the benchmark for stress testing. They're generated by a linear feedback shift register, an LFSR, and they are perfectly reproducible. The standard for full compliance testing is PRBS 31, which is a sequence of 2 to the 31 minus 1 bits.
Over 2 billion bits.
It's a long sequence, and PRBS 31 has specific properties that make it ideal for testing. It has a near-flat frequency spectrum, so it excites all frequency components of the channel equally, which reveals any frequency-dependent artifacts our CTLE or FFE might miss.
And it has a maximum run length of 31 identical bits.
And that long run of ones or zeros is absolutely crucial for stress testing the CDR and the slicer's ability to maintain its thresholds during long periods of low transition density. If the receiver's baseline drifts during a 31-bit run, it'll fail the PRBS 31 test, which indicates you need better low-frequency gain or a more stable CAS.
We've seen quite an evolution here, from static zero forcing to continuous gradient descent using LMS and specialized hardware correction with CES. But LMS still relies on a human-defined cost function, the MSE, and a mathematically fixed update rule. The next frontier in optimization moves beyond those fixed mathematical rules toward true data-driven global intelligence.
Reinforcement learning, or RL.
Reinforcement learning.
RL is the future of autonomous SerDes operation. It views the entire SerDes equalizer system, the CTLE, FFE, DFE, the whole thing, as a single agent that's learning optimal control strategies through trial and error.
All to maximize a defined performance metric, namely the data rate and integrity.
Exactly. This moves us beyond local optimization into true self-aware system optimization.
Okay, so let's define this problem in the language of RL. This is significantly more complex than a simple LMS loop. What does the agent observe? What actions can it take? And what is its objective function?
The problem space is enormous. The state space, S, represents the full observational snapshot of the receiver's condition. This is a high-dimensional vector, maybe 8 to 64 dimensions. It includes things like the estimated channel coefficients, the measured noise variance, the current eye diagram statistics like height and width, and instantaneous timing errors from the CRU.
And the action space is where the complexity truly explodes.
It is. The agent has to adjust all the tunable parameters at the same time. This means every FFE tap, every DFE tap, the coarse and fine-grained settings of the CTLE, those 87 combinations we talked about earlier, and the AGC level.
So unlike LMS, which adjusts taps independently to minimize MSE, the RL agent is adjusting the CTLE and the taps together to maximize the end-to-end BER performance.
Right. It's often creating an 8 to 50-dimensional continuous action vector.
That seems impossible to train conventionally. And what defines success? How is the reward structured?
The primary reward function, R, is all about maximizing data quality. So we define it as the negative bit error rate. By minimizing the error, you maximize the negative error. However, solely minimizing BER can lead to fragile solutions that are just barely compliant. So the sources suggest reward shaping, where we include a secondary objective, robustness. We give the agent a bonus for maintaining a large eye-opening margin.
So the reward function becomes something like negative BER plus a bonus for having a good SNR in the eye.
Exactly. This steers the agent toward robust solutions that are less likely to fail when conditions shift a little bit.
Which specific RL algorithms are best suited for handling this complex, continuous state and action space in a real-time hardware environment?
For getting the equalizer into the right operational regime quickly, researchers often use DQN, or deep Q networks. They use a neural network to estimate the Q value, which is the expected cumulative reward for taking a specific action in a given state. This is effective for solving the coarse optimization problem.
But for the stable fine-tuning and tracking mode, when you're targeting that ultra-low BER,
for that, algorithms like PPO, or proximal policy optimization, are preferred. PPO uses an actor-critic architecture. The actor learns the optimal policy, what actions to take given the state, and the critic evaluates the value of that state.
and PPO is prized for its stability.
It is. It uses a clipped objective function that prevents the agent from making huge, destabilizing policy updates in a single step. This ensures a slow, stable convergence toward that optimal 10 to the minus 15 BER target.
This is a radical shift. It means the chip is continuously running optimization experiments and adjusting hundreds of coefficients simultaneously based purely on empirical system performance. It's moving beyond deterministic signal processing into truly self-aware, continuous hardware optimization that might uncover equalization schemes a human engineer would never have even modeled.
That is the ultimate implication. By leveraging PPO, the SerDes can achieve performance targets that are impossible to design for purely with human-derived coefficients and fixed models, particularly in these complex, time-varying environments. It promises a holistic optimization across all system layers, CTLE, FFE, DFE, that traditional independent LMS loops could never hope to achieve.
That was truly a deep dive into the hidden algorithmic world of SerDes communication. We traverse the entire signal chain from the immediate pre-ADC analog conditioning, like the continuous time linear equalizer,
through the foundational digital cleaners, the linear FFE, and the nonlinear DFE, stabilized by LMS.
and all the way onto the advanced round of optimal sequence detection via Viterbi's algorithm.
We saw how the simple mathematics of LMS provides the constant adaptive intelligence needed to track channel drift, while the dedicated CAS hardware acts as that hyper-vigilant stabilizer against high-frequency voltage flutter.
And finally, we learned that reliable data integrity, even when you have persistent errors, relies on the multi-layered strength of standardized algebraic error correction codes like KP4 Reed-Solomon, which is capable of correcting up to 15 symbol errors per 10-bit code word.
I think what stands out to me is the incredible mandatory synergy that's required. It's never just one algorithm that saves the day.
No, it's the collaboration between a two-stage analog filter, a dynamically adjusted digital feedback loop, continuous threshold tracking, sub-picosecond timing recovery, and a powerful algebraic error correction code.
And they are all operating simultaneously at gigahertz speeds, collectively making millions of decisions and corrections faster than human perception can even register.
If you connect this to the bigger picture, the continuous evolution from hard-coded filters and local optimization algorithms like LMS to these sophisticated global learning-based equalization using techniques like PPO and deep Q networks, it shows us one thing.
The battle against channel physics and high-speed noise will increasingly rely on embedded machine intelligence. The complexity of modern multi-level signaling schemes like PAM4 simply demands this level of autonomous global optimization that can operate far closer to the theoretical Shannon capacity limit.
So given that algorithms like PPO can train an equalizer to optimize hundreds of parameters simultaneously based purely on the system's empirical bit error rate and measured robustness, like the I margin, will future chip design move entirely away from human-designed equalization coefficients and tuning methodologies, leaving the final complex optimization and long-term channel maintenance entirely to the chip's own learned intelligence? Something to think about as you connect your next high-speed device.